Okay, we'll take a little bit of a more careful look at this character pi 0, which was our first functor. Okay, what we'll see now is all completely elementary, and you would all have seen many ways of doing it, but the particular way is going to set us up for what we want to do later. Okay, so for a space x, we define pi 0 of x to be the set of path components. Okay, so that is to say pi 0 of x is going to be x divided by an equivalence relation, where I have to define the equivalence relation. Okay, so we define this equivalence relation, and what we'll do is, rather than simply defining the existence of a path, we'll look at all paths. So let's say our space is going to be a torus and a sphere, and I have a point P here and a point Q here, and I have a point R here. Then given P and Q, I have lots of paths between them, and I look at the set of these paths. But given P and R, there are no paths at all. Okay, so that tells you how we can define tilde. Okay, so we can define tilde in terms of whether the path is empty or not. Okay, that is in other words, we see that two points are equivalent if and only if equivalent in the sense of being in the same path component, if and only if the space of paths between them is non-empty. Okay, so you can think of paths as witnesses that these two are connected or not. And of course we need our main theorem here, which is saying that this is an. So we say that this tilde is an equivalence relation. Now how do we know this? We have to show that it's reflexive, symmetric, and transitive. And so let's look at it in terms of our spaces. So this is omega of x pp, and I have to show this is not empty. Well, this is because we can define EP in this, pp, and EP is given by EP of S is P for all S in 0, 1. Okay, so you take a constant path which just stays at P. So this is the first point, that it is reflexive. So it's a kind of effective way of showing reflexivity. How about symmetry? Symmetry is even nicer. So suppose we have P is equivalent to Q. This implies that, of course, omega of x PQ is non-empty. Okay, and then we define a function from omega of x PQ to omega of x QP. So if the first set is non-empty, so is the second set. Okay, so this is the function which will map alpha to alpha bar, where alpha bar of S is alpha of 1 minus S. Okay, and finally we have transitivity. So what does transitivity say? So transitivity is the statement, of course, that so P is equivalent to Q and Q is equivalent to R. So this will tell you of omega of x PQ is non-empty, as is omega of x QR. And it's perhaps time for a picture. So here we have P and Q. Suppose, well, I'll call this R prime now, it's no longer R. Suppose R was here and I had a path from P to Q. Then of course the path, and if this path was alpha and this path was beta, then the path is alpha followed by beta. But remember, we are parameterizing by 0, 1. So we have to go double speed. Okay, so for this, what we use is we use a map from omega of x PQ and omega of x QR to omega of x PR. Okay, and this is going to send alpha and beta to alpha star beta. And what is alpha star beta? So alpha star beta is going to be alpha going at double speed between 0 and half, and beta going at double speed between half and 1. Okay, so we'll look at this picture in a moment. So here we want 0. This is the point half. This is the point 1. We want alpha here. Okay, so you can think of beta of 2s minus 1 as beta of 2 times s minus half. So that will tell you why we get this formula. So between 0 and half we have alpha, except we go at double speed. So by the time we reach half, we have already reached alpha of 1, which we needed to, because alpha of 1 is beta of 0. That's what we had. And beta similarly goes at double speed, but given any point here, which is s here, we are only looking at this distance and doubling it. So that is s minus half doubled. So this gives you a product operation, and you can check that it's continuous, because where these two overlap, we use the gluing lemma, where these two overlap, alpha half, so alpha 1, sorry. So alpha star beta of half is going to be alpha of 1 by this formula and beta of 0 here, but we know alpha of 1 is beta of 0. Okay, so remember, we can only multiply paths provided we have one path, let's say a blue one, which begins at some and ends somewhere else, and then we have another one which is this purple color, which is of this form. Okay, so you can only multiply paths. They need not be embedded. That's a bit misleading if I draw embedded pictures, but we can only multiply paths so that this happens. Okay, so it looks like we have a nice group-like structure. That is to say, we have star, which looks like multiplication, and we have bar, which looks like inverse, and EPs, which look like identity, except they say there are a lot of them. So this is not quite a group. So not yet a group. And there are broadly two reasons why this is the case. And the first reason is that a star is partially defined. Now this might not be in fact a negative thing. You can think of this as a richer structure, a groupoid, and we will take that view here. But it doesn't directly give you a group, at least. This is easily fixed. So at this in this space, if instead of taking an arbitrary path from any point to any point, we fix a base point x0, and we only look at loops that begin and end at x0. Okay, so something like this. It could be anything complicated and begins and ends. Then we can always multiply it, and that's really what we'll be doing. Okay, after rectifying the second problem, which is the more serious one. But briefly, we can just fix a base point and just look at loops for that fixed base point, and that in that case what happens is that you see that you'll actually get star being fully defined. Also, the only sort of identity will be ex0. So we have many things that look like identities, but they are not quite identities. We'll look at groupoids briefly and see what in what way they are similar to and different from identities. But that is closely related to the fact that star is partially defined, because you'll recall that in a group, identities are automatically unique if they satisfy the identity property. Here, because it's partially defined, it's not unique. But the second problem is a little more of a serious thing, and we have to make a significant construction. There's a key idea in fixing it, which is that star so we'll etc. Do not satisfy group laws. And I'll be precise. So let me look at a couple of them. So first of all, let's look at E P star alpha, and let's assume here that alpha begins at P. Okay, so we have this thing. So then what happens to EP star alpha? EP star alpha is EP here first and then alpha here, while alpha itself is alpha. So these two are not equal as functions. Okay, so here I've taken alpha of 0 is P. They're kind of morally equal. One path is sticking to P for a while and then going along alpha, and the other is going along alpha, but they're not the same as functions. Okay, and similarly we do not have associativity. So if I look at alpha star beta star gamma, this is not alpha star beta star gamma. And that is because if I look at alpha star beta star gamma, first of all we have broken into two halves and called this part gamma, and then we break this into two halves. So alpha and beta go at 4 times the speed for only quarter of the length, and gamma goes for half the length. And here we have alpha going for half the length, and then we have beta and gamma for here. Okay, And then there is a third issue which is not formally an issue, but this is rather too big. There are too many paths. Mentioning that because it's closely related, we'll be fixing those two issues. The second one, which is formally of course an issue, and the third which is not, in the same way. So the thing is that we don't really have a group structure. We'll rectify this by introducing a key notion called homotopy. We have a partially defined product, and that is, well, either a feature or a bug depending on how you look at it. Okay, and we will address that as well by first seeing how we can deal with things in general, and we will to some extent deal with things in general, but mostly by specializing to the special case.